Section 4.2, solving system of linear equations in three variables. In other words, in previous section, we learned how to solve system of equations in two variables. Remember, we had like two equations and both had x and y in it. But now we're dealing with linear equation in three variables. A linear equation looks like this in three variables. You got x and y and z, and sometimes x and y would be missing depending on how the system looks like. But in general, a linear equation in three variables like x and y and z looks like this. Something times x plus something else times y plus something else times 4 is equal to a constant. Now, this is how system of linear equation look like in three variables. Remember, in previous section, we had system of linear equation in what? Two variables, so you had two equations. In this section, because you have three variables, okay, so they must give us what? Three equations. Two equation doesn't cut it. Sometimes some of the equations might be missing the variables. The fact that I have three equations, I know for sure what? I'm solving system of linear equation in three variables. So don't worry about, oh my God, how come this guy doesn't have x and z in it? How come this guy doesn't have z in it? It's okay. Sometimes in some of the equations, some of the variables will be missing, but it's okay. The bottom line is make sure you have what? Three equations given to you at the same time. So this setup is called system of linear equation in three variables. Okay, even though the first guy doesn't have a z, the second guy doesn't have what? X and z, but the third one got a z. So that kind of indicates you are in this section and you're trying to solve system of linear equation in three variables. Sometimes all the variables are present in all equations. Do you see it? Nothing is missing. X and y and z happens to appear in each equation. The solution of these guys, remember, sometimes they don't have a solution. Sometimes they have what? Infinite many solutions, but we'll do the ones which they have solutions. If they do have a solution, notice I said if any, the solution to these kind of systems is ordered what? Triple, not ordered pair, but ordered triple. In other words, you open a set of parentheses and follow the order of values of x and y and z. So first you write the value of x inside the parentheses, followed by y, followed by z, close the parentheses. That would be your final answer for solution of these systems if the solution exists. Sometimes there is no solution, but anyways. Suppose I give you a three, so-called order triple. Remember, order matters. This is x, that's y, that's z. The question is verify. Verify means show that this guy is a solution of this what? System of differential equation. Well, verify means what? Replace the x's with -5, y with 1, and z with 3 in all three equations. See if it checks. But for sure, the last equation checks because z is equal to 3, and yes, it is 3. But what about the first two? I'm supposed to replace this x with -5, the y with what? 1, the z with 3, and that's supposed to add up to -7. When you do, you get 5 plus 3 minus what? 15 equals -7, checks. But that's not enough. If you decide this is a solution, it has to satisfy what? All equations, not just the first or second or third, all three at the same time. Now you got to check the second equation. Replace the y with 1, z with 3, you get 2 minus 3. Does that add up to -1? Yes, it does. So the answer is yes. That guy is the solution of the system. Sometimes it is not the solution, like verify, or that means show if 1, 0, 1, remember the order matters, x goes first, followed by y and z, is the solution to this system of linear equation. I got three equations. In first equation, if I replace x with 1, y with 0, I get 1. Does that add up to -1? No, it doesn't. So stop. All it takes for one of these equations go bad, so therefore the answer is no, that's not the solution. Okay? So to review what we just said, if the order triple is solution, it has to satisfy all three equations. If it is not solution, all you have to do, check and see that it doesn't satisfy one of these guys, and then you stop. Then you can tell, no, it's not solution. There is no need to check the remaining two. All right, methods of solving system of linear equations in three variables. Remember, in two variables, we had what? Graphical substitution and elimination. Sometimes it's called addition. Here, we use combination of substitution and elimination. There is no graphical method that shows up in our calculus classes, advanced math classes, so graph doesn't apply. But we don't use just substitution, just elimination. We use combination of these guys. For instance, let's say you were asked to solve this system of linear equation. Remember, the word solve means what? Find x, y, and z. Based on the nature of this equation, I know what z is. There it is. Z is 3. So when it comes to solution, I know the last component is 3. All I gotta do is what? Find x and y, then I'll be done. So what I will do, I would substitute 3 into equations 1 and 2, correct? If you substitute what? Z right here in equation number, what was it? 2. So this is like 2. You get 2y minus 3. Remember, we already know what z is because they told us what it is. That's like our third equation. So immediately you can find out what y is. So move the 3 over. So you get 2y equals 2. So y is equal to 1. Now go back to equation number 1, correct, to find x. Right? So, so what would that be? Or you could, let me see, go to equation number 1. Yeah, we already know. So y is 1. We got that. But what about x? Well, only equation number 1 has an x in it. So I have to go here to find out what x is because I already determined what y and z is. So go back to equation number 1, replace the x with, y with 1, z with 3, see what x is. And when you do, x comes up equal to -5. So therefore, the answer is a triple, ordered triple, and x goes first, followed by z, y, and z, and this is our final answer. Remember, the answer is ordered triple. So x is -5, y is 1, and z is 3, and it should satisfy all three equations simultaneously. Sometimes some of the variables will be missing from your equations, like this guy. Notice z is missing from what? Equations 1 and 2. Well, that's not bad news. As a matter of fact, that's good news. Why? Because it's missing. So what you do, forget about equation number 3, pretend you are in chapter 4, section 1. Try to solve, so kind of group the first two equations. Notice they both have x and y. Pretend you are in chapter 4.1. This is system of equation in two variables. Do whatever it takes to solve for x and y. The way I did it, I said, oh wow, if I add these two equations just straight up, I get 4x is equal to 5 minus 1, which is 4, x is 1. Then I go back to equation number 1, and I found out y is what? 1. Then from equation number 3, which had a z in it, then I what? Replace the x with 1, y with 1, right here. And then I found out, oh my goodness, z is equal to 1. So the final answer is parentheses 1 comma 1 comma 1. Remember, that's your x, that's your y, and that's your z. Okay? So when some of the equations missing a common variable, that's good news. So you take those two equations which missing the common variable, form a system of linear equation in two variables, pretend you are in section 4.1, solve for x and y. Now go back and substitute those values in the third one. That's the only one with z in it. Find out what z is, and this is how you leave your answer. Do not box your answer individually. I did it so I can show you what my x and y is, but the final answer should look like this. Finally, you have equations, system of linear equations, which nothing is missing. These guys take time, so be prepared. It's not going to be like a quickie one with the last two. Once again, the word solve means what? Find x, y, and z. What you do in this case, when all three variables happens to appear in equations 1 and 2 and 3, you split the system into two separate systems. For instance, I took 1 and 2 and equations 2 and 3. Any combination will do. So you don't have to take 1 and 2. You could take 1 and 2 and 1 and 3. As long as you don't take the same equation twice, you're good to go. Once you split the system into two separate systems, now you have to decide which variable is it, common variable, from both of these equation system you like to eliminate. I decided to eliminate x's from system number 1 and 2. So remember, whatever you decide to eliminate here, the same variable gets to be eliminated there. You can't change your mind. So I decided to wipe out the x's, so I'm going to wipe out the x's here and here as well. So what do? In equation number 1, system number 1, to wipe out the x's, I multiplied both sides of equation number 2 by -3, so that way I'll get -3x plus 3x, it would add up to 0. So when I went through the multiplication, remember, whatever you do to the left, you do the same thing to the right. You get this. But now notice nicely that x's cancel, but the y's and z don't cancel, so you get what? 6y minus 3y is 3y, minus 6z plus 4z is -2z, and -6 minus 1 is -4. Call this equation number 4. Okay. Now go back to system number 2 and still wipe out the x's. In system number 2, what I did, I multiplied the top equation, both sides, by -2. Why? Because this guy was 2x. So if I multiply this guy by -2, -2x plus 2x, the x's cancel. So I distributed the 2, I got this. Then I coupled that with equation number 2, I got this. But when I add the equations up, x's nicely cancel. So combining the y's, I get 2y. Combining the z's, I get -5z. And adding up the numbers on the right, I get -5. So call that equation number 5. Now couple equation number 4 with 5. So what was the purpose of all these steps up to here? To change a system of linear equation in 3 variables to a system of linear equation in only 2 variables. Now we are back to chapter 4.1. Do you see it? You know what to do here, right? You can use substitution, graphical elimination. Turns out elimination is the most popular method, so I'm going to use that. So I decided to eliminate y's first. So I multiplied the top equation both sides by -2. And the bottom equation both sides by +3. So I can get -6y. And at the bottom I can get +6y. The y's cancel, correct? So when you go through these multiplications of -2 by first equation, 3 by the second, you get this. These guys nicely cancel. So you get negative 11z equals 11, so z is equal to negative 1. So now either go back to 4, so you are not allowed to go back to 1 or 2 or 3. Either go back to 4 or 5 and find y. I decided to go to 4, okay, right here, to find y, because I just found out z is equal to what? Negative 1. So if you go to equation 4, replace this z with negative 1, turns out y comes up to negative 3. Now you are allowed to go to either original equations 1, 2, or 3 and find your x. Pick your favorite equation right here, 1, 2, or 3, because you already know what z and y is. So the only thing you don't know is x. So pick any of these, because they all have x's in them. Pick your favorite equation, replace the y's with negative 3, z with negative 1, find out what x is. I went to equation number 2. I went here. Okay, so I had a choice of choosing 1, 2, or 3. I chose 2. So in equation number 2, when you replace y with negative 3, z with negative 1, this is equation number 2, x comes up to negative 2. Remember, we don't box the answer individually. We what? Put the answer inside the what? Set of parentheses, and we follow the order of how x and y and z should appear inside the parentheses. Remember, this is called ordered triple. Order matters, and you should have 3 numbers, and first number is value of x, followed by value of y, followed by value of z. Believe it or not, this point, this ordered triple, should satisfy all these 3 equations. And that should pretty much do it for section 4.2. Thank you.